In this fifth elementary particle physics video, we'll see how physicists in the 1960s attempt and understand and classify the jumble of hadrons and how those ideas led to the proposal that all hadrons are composed of even more fundamental constituents called quarks. Thanks in advance for watching this video. If you like this video, don't forget to like and subscribe to the channel and activate the bell. It is very important for the continuity of this channel. And if you have any questions or suggestions, leave them in the comments. By the 1950s, physicists were building a library of known particles. But something caught their attention. Leptons form a very organized family. 3 particles and 3 neutrinos, each with its antiparticle and a conservation law relating their numbers. Physicists believe that leptons are genuinely fundamental particles. On the other hand, the Hadron family was a mess by comparison, and hundreds of hadrons had already been discovered by that time. The table below contains just a small sample of hadrons. The number and properties of all the different hadrons became somewhat confusing, but some irregularities were observed among particles. Consider the family of mesons listed in the table below with spins of 0. Particles with spin quantum number 0 or 1 are called bosons. If we count both particles and antiparticles, there are 9 such mesons. Mesons of spin 0 form a nonet. We now consider the first 8 baryons listed in table, all having a spin of 1/2. Baryons are also classified as fermions because they have half-integer spin. The family comprises the proton, the neutron, and 6 other particles. This family of baryons form a octet. The family of spin 3/2 baryons contains 10 particles. This family of baryons form a decuplet. In each multiplet, the particles have similar masses. We are now going to improve our particle classification tables. First, consider the 9 lightest mesons that form a nonet. If we plot their strangeness versus their charge using a sloping coordinate system, a fascinating pattern emerges. The 6 mesons fit into a hexagonal array, with 3 particles at the center. The particles on the perimeter of the hexagon lie opposite their antiparticles, and the remaining 3, which form their own antiparticles, are at its center. Now we consider the family of the 8 lightest baryons, all having a spin of 1/2. If we plot their strangeness versus their charge using a sloping coordinate system, again, a fascinating hexagonal pattern emerges. 6 of the baryons form a hexagon, and the remaining 2 are at the hexagon's center. The groups of baryons and mesons can be displayed in many other symmetric patterns. For example, the family of the 10 baryons of spin 3/2 contains 10 particles arranged in a triangular pattern like pins in a bowling alley. Now let's summarize our discussion. Hadrons can be arranged in groups called multiplets, in which each member had the same spin and baryon number and other quantum numbers. First, consider the family of mesons with spins of zero. This family form a nonet. If we plot their strangeness versus their charge using a sloping coordinate system, as in the figure below, we can see that the particles on the perimeter of the hexagon lie opposite their antiparticles, and the remaining three, which form their own antiparticles, are at its center. Now we consider the family of the 8 lightest baryons, all having a spin of 1/2. The family comprises the proton, the neutron, and 6 other particles. If we plot their strangeness versus their charge using a sloping coordinate system, as in figure below, we can see that 6 of the baryons form a hexagon, and the remaining 2 are at the hexagon's center. The family of the 10 baryons of spin 3/2 contains 10 particles arranged in a triangular pattern like pins in a bowling alley. When we plot their strangeness versus their charge using a sloping coordinate system as we did above. Among the many attempts at understanding and classifying the jumble of hadrons, the most successful scheme is arranging the baryons and mesons into word geometrical patterns, according to their charge and strangeness. This scheme of classification of elementary particles is known as the Eightfold Way. Let's now discuss what led physicists to suspect that hadrons were composed of smaller particles. Early evidence of the internal structure of the nucleon was the magnetic moment of the neutron. A magnetic moment results from a circulating current, a motion of electric charge, but the neutron has no charge, or to be more accurate, no total charge. It could be made up of smaller particles whose charges add to zero, and this is evidence that the neutron has an internal structure involving a distribution of charges. Circa 1950, the first particle accelerators began to uncover many new unstable particles. Most of these particles are unstable and decay very quickly, and hence had not been seen in cosmic ray experiments. Could all these particles be fundamental? The Eightfold Way did more than merely classify the hadrons, but its real importance lies in the organizational structure it provided. But the very success of the Eightfold Way begs the question: why do the hadrons fit into these curious patterns? Other multiplets can be formed from the unstable baryons and mesons, but there are no observed groups of 3 particles corresponding to the triplet allowed by theory. Could there be a fundamental triplet from which all other multiplets could be formed? All these facts led Murray Gell-Mann and George Zweig in 1964 to independently propose that all hadrons are composed of even more fundamental constituents called quarks. In the original quark model, quarks came in 3 types or flavors, and they were named up, down, and strange. These quarks made up a triangular eightfold way pattern. The names of the quarks have no meaning other than as convenient labels. Collectively, these names are called the quark flavors. We could just as well call them vanilla, chocolate, and strawberry instead of up, down, and strange. All quarks have spin 1/2 and fractions of the charge on an electron. Antiquarks have opposite signs of electric charge, baryon number, and strangeness. Using the quark model, it is possible to describe all hadrons in terms of combinations of quarks and antiquarks. The quark model asserts that baryons are always combinations of 3 quarks, and every antibaryon is composed of 3 antiquarks. Mesons and antimesons are always composed of a quark and an antiquark. The properties of each hadron can now be explained in terms of the quarks from which it is made. The total charge of the hadron is the sum of the quark charges. The same can be said for the total baryon number and total strangeness. Let's see the quark content of 3 different hadrons: proton, neutron, and positive pion. The proton has 2 up quarks and 1 down quark. The charge on the proton is the sum of the charges of the 3 quarks. The values of charge add to 1, and the values of strangeness add to 0. The neutron is made up of 1 up quark and 2 down quarks. The charge on the neutron is the sum of the charges of the 3 quarks. The values of charge add to 0, and the values of strangeness also add to 0. The positive pion has 1 up quark and 1 anti-down quark. The charge on the pion is the sum of the charges of the 2 quarks. The values of charge add to 1, and the values of strangeness add to 0. Later discoveries added other flavors of quarks, called charm, bottom, and top. They were expected to have 0 strangeness, but they should each have a new conserved property of their own, namely charmed, topness, and bottomness, that distinguish these new quarks from the 3 original quarks. The properties of quarks are given in the table below. There is symmetry between the leptons and the quarks in that there are 3 families of each.